So, good morning. Glad to see that someone is coming today, even though it's Easter coming up. Some I see are already packed, but yeah, well. Anyway, today we are talking about complex objects and distributions. And there's actually two main topics today. And again, we have some literature that I actually should update. I have recently found a couple of new books that could be relevant. And yeah, also a large collection of papers that we can look on and websites. And until now on QBI, we have been looking at many topics. We are actually up beyond middle of the course. And we have been looking at data, we have looking at basic enhancements and how we can do the segmentation in different ways. We started also to look a little bit into how we can label the data. And now we are going to look into other ways how to describe and understand how the shapes of the objects can be measured. And so the things we are looking at mainly are skeletons, which brings us into the topic of tortuosity, and finally doing segmentation and looking at connected objects in the segmentation. And we have some different kinds of metrics when we are looking at our data. We can look at different point operations, looking at nearest neighbors to see how objects come together. I briefly swept over Voronoi tessellation last time, but that was just a brief hint on it. And we can also look at alignment of objects, and with voxels we can essentially do the same thing, and now we can also go on to doing 2-point correlation functions. Yeah, that was the only thing. And these are metrics that we can work with our objects and items. So now we want to know the topology of our objects, and until now we have only had, we know we have objects, or actually we have background, foreground, or something like that. We can also determine sizes of objects. We can know where they are, but how are they aligned to each other? And that is the thing that we are going to look into now. And for example, we looked at this segmentation of the cell map, where we can look at distance maps, which we looked at, which we had last week. And the distance map can actually tell us a little bit about the constellation, how the objects are related to each other. In particular, if we look at the distance map to background, we can tell the distribution of how far away different objects are. And if they are more densely packed, then you would have less of the long distances. If they are more sparsely packed, you will have more long distances in your histogram of this distance map. So this could be a way to start telling how the objects are related to each other. But we don't know so much about still how they can be connected, if there are groupings in different ways, and so on. And let's see. Actually skip this one. So we go instead on structure analysis, and here we already did last week. We could measure the area, perimeter, orientations, etc. And the next step in the structure analysis is to look at skeletons and also the advanced object labeling. And we saw previously that we have this component labeling, but that had the disadvantage that it couldn't separate items when they are so close that they are touching each other. And this is what we are going to address in the second part of today's lecture. But let's start first with skeletonization and networks. And in our world, we have different kinds of networks. We can have aerial pictures of urban areas, like we can see the streets in this picture, and this is kind of a network. In geology, you may look at pictures of rivers and seeing how the river is forming in the landscape, and maybe also what the shape is of a delta, maybe even looking at how the delta is evolving with over the years or over seasons, etc. And then we go in the soil, looking at roots. We again have some networks. And finally, also in biomedical engineering, you can look at blood vessels. In this case, I think it's a retina picture. And here we want to see how the blood vessels are distributed in these pictures. So all these have the same kind of abstract structure, and that is some kind of network. Some cases, these networks build loops, other cases not. So for example, the roads and rivers, they form loops. You can have, like here, an island, or you can have a city block where the street is closing in. But other cases, like the roots and blood vessels, you always have open-ended. You never have any loops in roots or blood vessels. So if you find loops in those images, you should be careful about what you're doing and maybe think about how you do the segmentation again or the tracking of the network. And yeah, that is more or less what this slide also says. One thing is that we want to look at is the tortuosity, which comes on a slide a little bit later. Another topic is branching. How often does the network branch? So split into more paths. It could be just splitting in two, but it could also be splitting in three. For example, if you have a crossing on a street, you actually have a three-way crossing, so you can go in three directions. Or sometimes in bad crossings, you can even have more. And then also for the root networks, and you can also see crossings in the blood vessel network. You can also see, no, not crossings, but branchings. And branching is a way in biology, to have a better coverage. And the more you branch, the stronger, for example, the root network is. It's better founded, it can cover larger area. And same goes actually also for the blood vessels. And yeah, there are a lot of examples on that. And the very abstract structure we can use to analyze these networks is skeleton. And that is a well-studied topic within image morphology. And the skeleton doesn't really look like a real skeleton, but it is the minimal structure that spans up the object. And it has, say, the relevant features of this pattern. You can, for example, see here that we actually have a little fork here for the ears. And the nose is only a single point, which actually is in this image. The only messy part is actually the tail, because there we have different call it fingers or the hairs of the tail. They give you a zigzag pattern, and that gives a more complicated skeleton to be able to reflect this complexity. Also the legs, they are also very simple. So in principle, you could say this is a horse, and if a small child would draw a horse, maybe it would come out something like this, possibly. Another one is we can look at the street map, take a little picture from this aerial image, and there is this street network database, so this is taken from there, where someone already nicely enough labeled the streets in these pictures. So we have the ground truth too to play with. But we are not going to use that in our analysis, more just as a comparison. So let's just do a little close-up. We don't have to be too many details in our example. So I just crop out a little piece here. I think it's about this area, which is cropped. And we still see we have 2 crossings and a main street and some houses. And the first step when we want to do this analysis is to first do some segmentation. And as you see here, we have a color picture. And the first step is to change it into a gray level segmentation. There are, of course, many ways of doing the segmentation, but in this case, I have chosen to use the HSV, so hue, saturation, and value color map, because here the value is actually telling us the position in the spectrum of the color, and that is for us sufficient to set a threshold in the image, and the segmentation looks like this. A bit messy, but what we can see is that there is actually one structure which is dominant and is significantly larger than the remaining small segmentations. And the remaining are probably houses, for example, this and that. What is interesting here is there is something coming across. It could be some text. Google has the habit of watermarking the pictures with Google, so it could be something like that. I don't really know actually, but there is something in the way, and that actually is a bit disturbing in our segmentation as well. So right now we used, as I said, the color space transformation, but we could also do some k-means, for example. Probably better result would be k nearest neighbor, but then we require training again, and so then we have to go back to the labeled data and for the segmentation, but we could do. K-means would have the advantage that then we would actually go on all 3 color channels in the segmentation, and then we would be able to distinguish different colors of gray. So I mean the house roofs, they are more like gray, and the street is, call it some brownish gray or reddish gray. So that would probably be captured within with the k-means. I haven't tried it, to be honest. So let's look at now our image, which was segmented. One way of sorting out the unwanted pieces is to do selection by size. And the first step of doing that is that we do a labeling. So we bring up the knowledge from last week. We use the label from scikit-image. And then we get an image like this. And we can see we have different colors for each object. Maybe a little bit difficult to see in today's light. And with a little bit of rescaling, we can also show it with the heat map. And there we have the advantage of seeing actually the numbers for each label. So we have 0 is the background, and then apparently we were lucky to get the main street here as 1. So then we will essentially sort out this piece by saying we want an image with only the ones in it. And that is what we will work with. So the skeletonization, there are different ways of doing it. And one way is distance transform. Look at the distance transform, we will see, so let's see here. So here I first select the label 1, and we compute the distance transform, and from that we get this image where we have first the main road component, and if we compute the distance map of this, you can see that the middle of the structure is essentially the skeleton that we are looking for. So and here you can also see the values, but it's some kind of ridge, and the values fluctuate. We can't really put a threshold on it directly. Instead, we would do something like computing some gradient information. In this case, we do a Laplacian, and the approximated kernel for the Laplacian is that we have a central value 8 and surrounded by a lot of -1s. There are different approximations to the Laplacian, but this is a common one. And looking at the result from that, we see quite nicely that the ridge is now marked up in blue, or actually all the ridges, because we have some interesting branchings here. And that is what we can use now to detect our skeleton. So what we would look for is, for example, local minima in this, and that will help us to find our skeleton. The red ones are positives, and we actually don't care much about those. And now we want to do a skeleton, and the idea with this is that we actually have two values. We can look at the minimum distance, the threshold, the distance image by some minimum distance, and we can also combine that with a minimum slope, and that would be looking at the combination of both the gradient and the distance map. Let's see. I think I have something calling outside. So with that, we would have some distance, which is the top. So we have this tuple of both distance image and Laplacian image, and then we do our skeleton setting a 1 if two criteria are fulfilled, and looking at the bivariate histogram of the two informations, we can see that with our thresholds we may consider all the ones in the red box here to be our skeleton. So we want to have a certain distance to fulfill it, and we also want some value on the Laplacian. Yeah. And the resulting ridge skeleton, we use for that function and also in scikit-image in the morphology section, I think. That is a bit stupid now. Called medial axis. There are different algorithms to do the skeleton, and some with different properties and what they look like. And our Laplacian distance looks like this, and if we do this medial axis, we get this kind of skeleton. It's a minimal structure, but thanks to all the variations in the surface here, you can see that there are bumps all over the skeleton. We get all these spurious branches, which we actually don't want to have. So next step is to done. And yeah, there are a lot of different algorithms for doing this. There are different called, for example, thin function, also skeletonize, and some of them they are working in iterations. So in principle, it's doing a lot of erosions on the gray level, no, on the black and white image. So it erodes until it reaches some kind of minimum criteria. Either it's number of erosion iterations, or else it is that the surroundings only have a single pixel. So that can be used for also for the skeletonization, and depending on which algorithm you use, you can get more or less clean structures. And exactly which kind of skeleton depends on the shape of the objects, how clean the surfaces are. I can't say that one is better than the other one. It depends on the way your data looks. So here we have the basic segmentation. We can do the morphological thinning. That's a single iteration. Then it looks like this. It's actually just eating off, I think, 1 pixel or maybe 2 pixels in the width. Then we can do some opening. And the idea with the opening here is that we can remove some of these unwanted features. So looking at particular here and here, you can see that with the opening, you can remove some of these irregularities along the edge. And after that, we can get a much nicer skeleton than we had before. We had that one before, and now the complexity has reduced quite a lot. Now you see a couple of loops in this skeleton, and the loops, they are caused by small holes in the segmentation. To avoid these loops, what would you propose to do? Assuming there shouldn't be any, so. Yes?
The way I see it, they stem from those single pixels.
Yes.
Are at the start there, so
Yeah.
we can somehow fill those out.
Yeah.
And we don't get the loops.
True. Do you know operation to do it?
I mean, I don't know if it was already in the lecture, I don't remember, but
It was.
I mean, if the 4 surrounding pixels of this pixel are filled a part of the structure, then
So if I say a morphological closing,
is that with 4 pixels?
oh, it's so many pixels as you define it to. Yeah, so the closing would do a dilation, which would close the hole, but then the whole structure would grow, and then it follows it by an erosion, which shrinks it back. But then, when you erode, then this hole is filled, and you have reached your purpose. So we could, in principle, here now add clean up loops. But now for the following steps, I want to have the loops just to show a little bit effects. And one thing we want to look at is to see what our junctions between the different branches, what they look like, or identify them for the first. And one way of doing it is to compute the convolution with a box filter, a 3x3. And with that, we actually count the neighborhood around each pixel. So if we do the convolution around on the skeleton, then you can see we have, of course, a little bit of fatter skeleton, but there are some interesting features here. You can see that it turns from green to blue, and sometimes we also have gray here. And now it's 1 pixel wider because we did this 3x3 filtering, but then we can actually just mask taking the pixels from the skeleton and extract those pixels, and we get this image. And the resulting skeleton now has, at the endpoints, are blue. Then it's a bit hard to see, but the junctions, they are more like gray, and the remaining skeleton is green. So we have now actually, in principle, labeled different structural items in the skeleton. And looking at that, that I should have reduced. So looking at a close-up, now you can see that the main skeleton branches, they are number 3. Then we have a 3-way crossing. No matter which way it's oriented, is always a 4, because what we have is the sum of 4 pixels in the neighborhood. And if you have a 4-way crossing like here, then it's 5, because you have the central pixel plus 4 pixels. And there are some confusing cases where it could turn a 3-way crossing into a 5, but there are none of those here right now. Yeah, this, for example, this 4 is a bit confusing because I would say it's already part of the branch. But thanks to this 90-degree turn here, it becomes a 4 as well. Endpoints turn out into number 2 because you only have a single neighbor. And with this way, we can actually start characterizing and counting how many endpoints, how many crossings. And this is a type of analysis that can be done using this labeling. So here is everything is split up into the different levels. And here we would have 5 different cases. So if you have a single neighbor count equal to 1, then it's an isolated pixel. If you have neighborhood count 2, then we have the endpoints. Neighborhood count 3 is essentially line segments between the different junctions. And then we have count 4 and 5, they are different multi-way junctions. If it's 3, 4-way junction, that's still to tell. So with the help of this simple operation, the convolution, we can actually do a nice analysis of our skeleton. There are also different ways of doing the kernel coding. Until now, we use just a uniform filter. But if you want to know more about orientations, you can do a kernel coding like this. And the advantage is now you can actually see the neighborhood as a chain of bits in a 9-bit number in this case, actually. If you include the central pixel, it's a 9-bit. And as it's going around like this, you can do like a bit chain analysis and see if you have these L-shaped junctions that we had in one place. That can be identified using this kind of kernels. And of course, the analysis is much more complicated, but we can also tell if a pixel is touching the skeleton or if it's on the skeleton by just thresholding between 256. If it's greater or equal to 256, then we are on the skeleton, and if it's less, then it's outside of the skeleton. And of course, the box filter has much simpler numbering strategy, but here you can really see how the pieces in the skeleton are oriented. And again, depending on the type of analysis you want to do, the precision in the interpretation, it could make sense to use these J4 and J8 convolution kernels. As we already saw, our skeleton was a bit messy. We had a lot of branches. It should be, in principle, only a street with 2 side streets. But we had a lot of small little branches in the skeleton. And now we can do some pruning. We could have some kind of model base that it's not allowed to branch too often. We can also look at minimum branch length, saying that if a branch segment is only 2 pixels long or 3 pixels long, then we reject it. Can also say the minimum branch width. We had the original, we had, for example, the distance map, and if you project the distance map on the skeleton, you can tell if a pixel is far away from the border or not. And that can also be used, and then we can have multiple criteria to determine which is the right pixel for the skeleton. So for doing that, we need first to label our segments. So now we use again the box plot, box filtered skeleton, looking for all items that have a label 3. Do some coloring and plotting, and then we can look at the label length, looking at how long is each segment in this for each label. And here is a histogram of it, and we can see some segments are clearly very long, and others, they are averaging out to some level, so it's not so easy to identify actually. So we have many less than 10, and some few going up. So let's say we want to threshold our skeleton at some level of length. That comes on the next slide, I believe. Yeah. And we say we want here to have the label length should be greater than 5. Everything else we reject, and then we want all the pixels that are masked as endpoints and also masked as something that is larger than 3 in the mask. So that would be line elements and junctions. And the pruned skeleton from that is like this. P.S. we have some endpoints in the skeleton, which we could probably clean out if we want. And finally, we have our pruned skeleton versus the ground truth. And as you can see, we still have some strange things in our skeleton, but this one, for example, is probably some kind of street, but it's not the main street. This piece here is from this artifact in the acquisition, but we are not far away from the true truth, actually. And then we can doing again analysis of maximum segment width. Then we look at these different segments and look for the maximum width within each segment, and then we project on the skeleton, and we can see that there are some very long or wide segments around here. Some green ones, they are mid-sized, and brown ones, they're also quite wide. So you can see actually here that on the main street, it's wider than the side branches. So these, for example, they are quite small here and here. So maybe we could do even a filtering on the maximum width in our skeleton. And this is also shown here that we have some which are not so wide, and the main part is between 5 and 9 pixels wide. Actually, this is half width, because we look at the distance transform. And then we can do the pruning again, and doing it based on the width. Here we do the threshold. As we saw, there was a gap between 4 and 6, or 4 and 5. And so set the label width as 4.5, and then we continue with that, and we see what the pruned skeleton looks like then. And we are getting even closer. We don't have any of these small items around anymore. And this, I think we finalize as our final skeleton. And that, compared to original medial axis skeleton, is quite an improvement. As it appears, you may have to live with some misclassified branches, but that can maybe also be added on other informations further on, depending on what you're doing. And then from this, now we can look at some topology in the image. We can look at different segments. We can look at junctions and endpoints. And from there, we can do some analysis again on the skeleton, looking at our projected map. We can see here that we have, in our street view, we have a junction. This one is kind of a misclassified junction, but it's probably there is some branching in the segmentation. And here we have a junction. There are some thing going out here, but in principle, we can see our junctions, endpoints. They are blue, not so visible, but we have some endpoints. You can see here, here, everywhere. I should change the color map, it seems, because it's not doesn't come out very well here. So now we still only have our endpoints and line segments, and we want to get an idea of how the network is connected with each other. And for that, we want to have a little example, a little toy example, where we have two images, one image, which consists of node, edge, like this. And in this example, we can label the nodes like this. We have node 1 and 2 and background. And we have edges 1 and 2 as well. And now we want to look at which elements belong to the same, which edges belong to the same nodes. Other way around. Which nodes belong to the same edges. Sorry. And I think I'm at the end. Yeah, I am. So this requires some code. There is a mix of visualization code and actual code. I haven't cleaned that up. But what we see now is the important thing is we have our image up here, would be some kind of skeletonization and node analysis. And the next step is to label all the nodes and label all the edges. And then what we're doing is also doing some growing with the help of dilation on the nodes equal to 1 and the nodes equal to 2. And the result is that we have to do some, yeah, that's a bit messy one. I'm not going to explain this code. But in principle, what we are doing is that we go through each label. That one should have shown up. There it is. That was what I was missing. So now we can see the result of that code. So what happens is we have our label nodes, and if we grow the first node, we can see it turns out like this. And that one only involves edge 1 here. If we take node 2 and dilate it, you can see that that would actually include both edge 1 and edge 2. So we would have edge 1 here and edge 2 here. So this node 2 would actually connect that segment with that edge segment with that edge segment. And that is the kind of analysis we are going to do now with the next. That is doing it on our skeleton on the street map. And this should have been hidden. So once we run it, we see here which edges are connecting to which nodes, and get a nice little map here. And afterwards, we can see that we have this connectivity map, which tells which nodes are connected with the help of an edge. And then this map tells how complicated our network is. If you would have a very simple network, it would be very narrow. the more complicated the network is with more branchings, the wider it gets. So you can even see here that when it blows up into a cross like this or like this, then you are probably at a junction in the network. And another information we can look at is the skeleton tortuosity. And that is the ratio between the length between, let's see that I don't not mixing it up, but it's the length between the points, the endpoints in the skeleton element and the curve that it draws. And with that ratio, we can tell how complicated the network is. So if you remember, for example, the blood vessel network where we have a lot of curves in it, comparing that to a street network, which are mostly straight lines, then you would have a lower value on the blood vessel network than on the street network. And here we can see, no, not yet. That is on the wrong place. So here we can see the tortuosity for different items, and some items, most of the items, they are lying around this 0.85 average, and then there are a few ones that are really curvy. They come down here to these places. And then we can also look into other ways of visualizing the network. We use randomly organized graphs. That's way of reducing a bit of the complexity and seeing, making it more compact in a way. And you can have the network a little bit compact and visualized. Each node here is labeled, and this network would correspond to that one. Sometimes it makes sense to visualize it like this. We also, you can see here, is color coding on different things. So we have the width, so we have the length, is color coded on these different parts of the network. Graph analysis, let's see, what do we have here? Yeah, then we can also look at the different number of connected edges in our network. We can see that most of the street elements, they are have a simple connectivity. It's a bit annoying. Matplotlib shifts the numbers a bit strangely in the histograms. They should actually be, this should be 2 connectivities, so the 2 should be under here. With some Matplotlib magic, you can move the positions, but that's a bit annoying that we have to do it like this. And final thing before I let you off to break is skeleton 3D. What I've shown until now is only 2D skeletons, but we can do exactly the same thing in 3D. Also, again, with the criteria that the object topology must be preserved. And the other thing is that analyzing the nodes, the network neighborhood is more complicated, because now, instead of just looking at 3x3 neighborhood, you have a cubed neighborhood. And then, for example, this bitwise labeling that I did before doesn't really work well, because there are relations that are not so easily to cover with single bit shifts. So you have to look for different ways of doing it. Skeletonization in 3D is also another complication, because you can have single junctions, so you can have the criterion that you only create lines, segments in your skeleton, but there are some skeleton algorithms that actually also project planes instead of junctions, so they add that complexity too in the structure of the skeleton. Here is an example that we looked at the root network. So it's tomography of a root. And we want to look at, see how the root shape under different growth conditions, and see how the water uptake works. And what we needed to do was first to segment it. That was done using some machine learning algorithms. And from there, we can look at segment lengths, we can look at branchings, branch orientation. Some plants prefer to grow along the soil surface, other ones go deep down. And also looking at the influence volume of the root network. All that can be done using this analysis. And typically, each slice doesn't give much information. We only have very thin items. And then we can look at the roots as a projection in one direction. And then we can see what the root network looks like. And that can, of course, also be skeletonized. Again, with scikit image, you can do skeletonized 3D on the root network. And here you can see what the skeleton looks like. I don't know if that is a loop or not, but in the root network there shouldn't be any loops. So I hope it's not. And now it's break.